So this is where we're going to start to deal with a circuit like this one, or any other combination circuit. The circuit on the left doesn't seem to fit what we know about series and parallel circuits. It's not a pure series or parallel circuit. Looks like there are three parallel parts. We have a resistor in series with a battery. The other problem with this one is I have two batteries that I cannot add together and resolve to one battery. So this one would not work with our process of combination circuits either, because I can't add those two batteries. Which one is the power source? There's no way to get that to work out. So what do I do with this one? Well, it happens to work out that there's a solution to that. And that solution is what's called Kirchoff's rules. And Kirchoff's rules are a statement of basically two rules that allow us to begin to solve out combination circuits. And this works particularly well with combination circuits with multiple power sources or multiple different types of things in the circuit. So if you had not just resistors, but other types of electrical devices that we won't study in this class, capacitors or inductors or diodes or things like that, Kirchoff's rules is a good place to start. So what are the two rules? The first rule is what's called the loop rule. And what it says is for any closed loop in the circuit, you can add up all of the drops in voltage. It has to equal all the gains in voltage. The loop rule is essentially a statement of conservation of energy. That if you have a place where energy is gained by charged particles in a circuit, that energy must be lost somewhere else in that closed loop. Now there are two ways to do a voltage drop. One would be going through a resistor in the direction that current is defined to go. That means that you're going from the positive end of a resistor to the negative end of a resistor. That's a drop in voltage. Or the other way is to go across a battery from positive to negative. Voltage decreases as you go from the positive side of a battery to a negative side of the battery. Now voltage gain, there are two ways you can do voltage gain. The most common one is to go across a battery from negative to positive, the way current normally would flow. The second way would be to go through a resistor opposite the direction you've defined current to flow. So voltage gains happen in batteries in the direction of current. If you go opposite the direction of current through a battery, it's a voltage loss. Voltage losses happen in resistors in the direction current goes, but if you go the opposite direction of current in a resistor, you gain voltage. Now we'll work some sample problems where this definition becomes important. In this particular problem, we can actually make batteries voltage gains, resistors voltage drops, and call it good for the most part. The junction rule says at any junction, and there are two junctions here, here and here, the current into the junction must equal the current out of the junction. This is really a statement of conservation of charge, that you can't create or destroy charged particles at a junction. So let's apply Kirchoff's rules to these circuits, and I think what we can do is try to find the current through all three parts of this circuit. And there's really three parts that could have current. This part here, which I'm going to call I1, that part in there, which I'm going to call I2, and I've defined I2 to go to the right. The reason why I've defined I2 to go to the right is that this battery looks like it's pointing this way, and it looks like it's bigger than this battery, which would be going that way, and so the current probably goes this way through this resistor. Now if I guess this wrong, we'll get a negative number for I2, and we'll just say, well, I guessed it wrong, it's the opposite direction. And I'm going to say I3 through that battery, which it pretty much has to be going that way. So if I look at that junction or the other junction, we can get the same statement, I1 plus I2 equals I3. And then there are three loops we could conceivably use. The outside loop, so starting down here, V2 plus V1, my voltage gains, equal my voltage loss, I1 R1. Sometimes I'll write this as V1 plus V2 minus I1 R1 equals 0 as another way to do it. There's what I call the top loop, which really we could start here. I have a voltage gain, V1, a voltage loss, I1 R1, and then I have a voltage gain, R2 I2, because I'm going in this loop opposite the direction of current through that resistor. Now for the bottom loop, that's pretty simple. V2 my voltage gain, I2 R2 my voltage loss. There we go. So what I've created now is a series of equations. I have three equations here. And it happens to work out that I can solve all three of these equations for Actually, I have 4 equations. I can solve them for the 3 unknowns. So what I'm going to solve first is the bottom loop one, because it's the simplest of the ones. If I divide both sides by R2, I find the current going through here must be 6 amps. I'm going to solve the top loop one, V1 plus V2. Divide that by I1, and I get 2 amps for the outside loop. Cool. And then if I add I1 and I2, I get 8 amps for I3. And so there we go, I've solved the currents in all 3 parts of the circuit. So the advantage to Kirchoff's rules is you develop a series of equations that you can use to solve for unknown currents, or if I didn't know one of these resistors, I could conceivably have an unknown resistance. Maybe I don't know how big R2 is. I think you can actually solve it out by not knowing how big R2 is. Nope, you would need to know R2. You could not know R1 and be able to solve this out. Or pretty easily without R1, because, well, you have 2 unknowns. 2 unknowns, you can solve for R2, we could maybe get something about I3 and then work it out. So there are ways you can work those types of problems out in that type of circuit. We'll definitely work some problems like this. This is something that I think takes practice, and I think what takes practice is developing these equations here.